So to test this, we need a special kind of setup. We're going to want two of these modems talking to each other and communicating on a normal 5 megahertz channel. And then we're going to want to introduce this minus 41 dBm thing at, I believe the frequency is 929.7 megahertz from the spectrum analyzer up there. And the power level is minus 41 dBm measured here. So this will be the interfering thing relative to what a regular modem would be receiving at the same time as it's receiving a signal from its remote partner modem. Okay, so we'll put the receiver over here. So we'll have one modem receiving here and have another modem transmitting over there. Now, how do you inject a signal into the middle of this in a coaxial system? These power levels are kind of high, and you don't want that power going to both modems because it'll screw them both up, and that might have an adverse effect on what you're trying to measure. You just want that power level reflected on one end to maximize your control. So first of all, you can't run a 1 watt transmitter into one of these receivers. You'll just blow up the receiver. The maximum safe level here is 0 dBm, but I think general wisdom says stay below 30 or 40. So we'll want a lot of attenuation on this path. So here on the transmit side, we can vary this power level a little bit, but we can use these here. We can use these attenuators, and I think that's a 30 or a 20. I've also got some 60s. So let's say these modems are comfortable transmitting from, I don't know, plus 10 all the way to plus 30 dBm. Okay, so we've got roughly a 20 dB dynamic range to work with. And what we want to produce here is something, let's say, less than minus 30 dBm. Okay, that's the absolute max we want to shoot for. So I've got some 20s and 60s, or I've got 120, 130, and a couple 60s, I think. So seems like a simple thing to do would be to slap a 60 on here, and then you go from plus 30 all the way down to minus 30, or maybe drop the power here a little bit, and then you're even lower. But the problem with that is, where do you inject the signal, right? Because as this receive modem is talking to that one, it will want to transmit back. This will be a full bidirectional communication. It's not just unidirectional, because we want to see how the packets and acknowledgement packets are affected. The data and acknowledgement packets are affected. So we can't simply just use 160 dBm. So let's split that up a little bit. So here, let's use a minus 20 dB in front of this guy. And here, let's use a minus 30 dB. Okay. And in the middle, well, these are joined. In the middle, we don't want to just wire them together because we will want to inject a signal. So we'll need some kind of a T connection in the middle, and this will be our T connection, ZAP-D21, which is a power splitter and combiner. But it's got a special well, not special, but it's got an important property in that whatever signal it receives here, it has a high level of attenuation, as in it does not pass that signal back to this port. Whatever signal comes in here, it only passes the signal forward. Now whatever signals come in here do pass over to that port, and that port equally. So if we stick one of these in line, let's draw that here. We have that going there, and then we have another signal there. And this will be the combiner. We will want to protect whatever's injecting the the signal here from excessive power coming from this guy transmitting back, right? So if he's transmitting at plus 30, let's say, minus 20, that's still plus 10 dBm. That would potentially go back to your signal source, which is bad. So there's another little piece of magic available here in the lab. Let me just free this up. I'm not sure if this has a product number that's recognizable anywhere or not, but basically this is 2 isolators back to back, which have a very good, well, amount of isolation. So I can measure that and figure out exactly what that isolation is. And well, I have no idea what the symbol for an isolator is, but let me just write isolator here. Okay. And then finally, the signal source and the ground reference. So for the signal source, just a regular signal generator, feeding an isolator to prevent any kind of back feed here, and disturbing this signal source, going over into the combiner, and going over to the received modem. So what you should have is packets coming through here, added with that interference signal, and all of that mess being sent to the receive over here. Now if you want to see a proper level of interference here, we're shooting for minus 41 dBm interference, right? You'll need a certain level of signal here, but there's going to be loss in connectors and in each one of these units, right? We know this loss is going to be minus 20, right? So we know that we're aiming here for an interference level of minus 41 plus 20, so minus 21 dBm of interference signal here. Going through the combiner, we should measure that loss, whatever that is, and going through the isolator, we should measure that loss. So we'll want something a little stronger than minus 21 coming from this signal source. So let's do these measurements and figure out exactly what signal level is required.